Welcome back to another episode of Dave Does Math from Home. This is part 2 of our video series on gradients and directional derivatives. Our first video went into a lot of depth about the theory behind gradients and what they meant and what they're used for. So now we're going to do some examples of gradients, and hopefully that will prepare us really well to talk about directional derivatives, which are a little bit more exciting than partial derivatives. So I have a function here. It's some sort of cubic something or other. I don't know what it's doing, but I can find its gradient. Remember that the gradient of f always means partial with respect to x times I plus the partial with respect to y times j. And so the partial with respect to x here should be 3x squared minus 4y I plus partial with respect to y here should be negative 4x plus 3y squared j. This is the gradient of f. So not super complex. We already know how to take partial derivatives. We're just creating a vector valued function out of them by attaching i's and j's to the various gradients. Let's do another example, except let's do some three-dimensional stuff. Let's say f of x, y, and z is x squared. No, let's do 27 minus x squared minus y squared minus z squared. So now we have a even higher dimensional function. This is different from the functions we've dealt with before because now we have f. F is a function of x and y and z. So now, in this function, x and y and z are all independent variables. You can, at any point in 3 space, you can choose that point x, y, and z, and you can plug it into this function to get something. Maybe this is a density function. Maybe this will tell you the density of a certain object at this point within that object. Maybe it'll tell you the temperature of something. I don't know. I have no idea what this represents. There are a couple different things we can do or a couple different practical applications for using x and y and z all as independent variables and having a function give you a fourth value at that point. I'm not really concerned with the applications at this point. I just want to show you how to do a gradient of a 3-valued function. So you can hopefully probably guess how the gradient goes. The gradient should be the partial derivative with respect to x is negative 2x. I attach that to I. The partial derivative with respect to y is negative 2y. I attach that to j. And the partial derivative with respect to k is, or sorry, the partial derivative with respect to z is negative 2z, and we attach that to k. So this is now our vector space. At any point on or at any point in 3 space, this will tell us that the vector is pointing inward. This is sort of like a black hole vector we talked about before, except the farther away from the origin you are, the stronger it pulls you in. And when you get really close to the origin, it pulls you in very weakly. So this is gradients in 2 space, gradients in 3 space. Again, finding the gradient itself, usually very straightforward. We know partial derivatives. Just attach i's, j's, possibly also k's, to the different pieces of your partial derivative, and bam, instant gradient. Which means I think it's time to talk about directional derivatives. So, I'm going to go back to the original example for directional derivatives. That's the one that I drew out, and that's the one I think we can visualize perhaps the easiest. The original example was f of xy equals x squared plus y squared. This is a very nice friendly paraboloid. Starts at the origin, goes up in a round fashion in all directions. And we already know that the gradient is 2xi plus 2yj. And we know that if we tried to graph this gradient as a vector field, we're going to get like a starburst, sunburst pattern. It just goes out in every direction. Or I guess sometimes they call that the explosion vector field. So we know what the vector field looks like. We know what the graph looks like. Vector field just goes out in all directions, straight away from the origin. So here's the big question. I'm going to draw that bigger so that the big question is more clear when I ask it. I know that I'm going out in all directions. Okay, I have this explosion pattern, the sunburst vector field, and I know that these vectors, the gradient vectors, they always point me in the direction of the steepest ascent. So in the last video I talked about imagining yourself standing on the surface of this paraboloid. The gradient will tell you the direction of the steepest ascent. If you reverse that, that'll be the steepest descent. And if you go perpendicular to that, you'll be walking around the level curve because you will not be ascending or descending at all. But then the question is, if I'm standing here, I know that the steepest descent is this way, I know that the steepest descent is that way, I know that if I go around, I'll have a level curve. What if I want to go this way? What if I want to go straight up? Or what if I don't want to go, what if I want to go vaguely west by southwest? Not straight into the center, but kind of crooked off into the center. The question becomes, how steep of an ascent or descent would I get moving in this direction from this point across this surface? And this is where we really get the idea of directional derivatives from. When we first started talking about partial derivatives, I was saying that when you take the partial with respect to x, that's you moving straight across the x-axis. There's no variation in y. You're just moving straight in this direction. This is fx. And when you take the partial with respect to y, you're moving straight up in the y direction. There's no variation in x. That's what lets us treat x and y as constants when you were doing the partial derivatives for the other piece. But if we want to move in some combination of x and y, if we want to move along this vector, that's really what the derivative is for. It's the purpose of the derivative is to tell us the slopes of the function at certain points. And so the directional derivative is what's going to allow us to move beyond strictly horizontal or strictly vertical movement. So we can, at a point, we can decide to move in any direction we want, and we can still figure out the slope along this surface of moving in that direction. So that's what it's for. Let's talk about how to do it we'll use these examples here. So the point I have chosen here, let's say that point is 2, 2. So we're at 2, 2. The gradient of f at 2, 2 is 4I plus 4j. So I know about this vector. This is 4I plus 4j. And you can always find these specific gradient points by you get your gradient function, you plug in the point you're interested in, and that will give you the gradient vector at that point. So that's a pretty small step. Nothing mind-boggling has happened there. I'm going to switch to a different color for this other vector so I can distinguish between the two vectors I'm interested in. Okay, so let's do the red one first. The red vector is pointed directly up from this thing. So this red vector, this is me moving, we'll call this one U. U is, we'll say 3j, straight up. Yeah, 3j is fine. We're moving straight vertically. I want to find how much steepness implied by this corresponds to this. And the steepness that you get here sort of matches this insofar as these two vectors point in the same direction. If they point in the exact same direction, then great, we know how to do that steepness. If they point in opposite directions, then we're going to get a lot of unsteepness. It'll be negative. And if they point in perpendicular directions, that will give us the level curve. That should give us 0. Fortunately, we have a tool that will measure the same directionness of two vectors in such a way that it'll give us positive numbers when they're pointing in the same direction, and negative numbers when they're pointing in opposite directions, and 0 when they're perpendicular. And that tool is the dot product. So the basic idea of directional derivatives is the dot product between the gradient at a point and a direction vector that you're moving in. The problem comes in, as the problem often does with dot products, the problem comes in terms of magnitude. Moving 3 units directly up from this point should not give me a different answer than moving 15 units directly up from that point. I'm not actually moving that entire distance. I'm just pointing in this direction and trying to look at the steepness at this point. So the magnitude of your direction vector needs to not matter. And the way we make that magnitude not matter is we transform it into a unit vector. So if u is 3j, the magnitude of u is pretty obviously 3. And that means unit u should just be j. 3j divided by 3. So that's the thing there. The magnitude of your gradient reflects the steepness there. So we need that magnitude to stay intact. We're not going to mess with the magnitude of the gradient. That's going to tell us the steepness. But we do need to mess with the magnitude of the direction vector. All we want from that is a direction. We don't want magnitude to be involved at all. And so we always have to transform that into a unit vector. Once we have this thing as a unit vector, we just take the dot product. The directional derivative I'm going to write the whole thing once, and then I'm going to shortcut it later. The directional derivative of f of x, y at 2, 2 in the direction of u equals 3j is unit u dot the dot product between the unit vector, the unit direction vector, and the gradient evaluated at the point. So for us, that is j, if we're going to write this in brackets, j is 0, comma 1, gradient of f is 4, comma 4. So this dot product is just 4. So if you're standing at this point 2, 2 on the inside of this paraboloid, and you're looking at moving straight north, the steepness is 4, which is a slope. That's the slope of this surface in that direction at that point. So this is how we tie the idea of derivatives back into slopes. We can do directional derivatives in any direction we want, at any point we want, using the dot product between the gradient and the direction vector. I'm going to see if I can do the green directional derivative real quick. Let's say this is v, and v is negative 2I minus j. First I need unit v, so I need to find the magnitude of this, and that should be the square root of 4 plus 1, so that's root 5. So unit v will be negative 2 over root 5I minus 1 over root 5j. This is my unit vector, and so the directional derivative at this point in this direction is the dot product of unit u times the gradient. So this will be negative 8 over root 5, sorry, not plus, minus 4 over root 5, which is negative 12 over root 5. Don't know what that is. Probably 5-ish? No idea. But this is the fast version of the process. You get your function, you find the gradient, you evaluate the gradient at your point to get a gradient vector instead of a vector field gradient. You want the specific vector, no x's and y's left anymore. You transform your direction vector into a unit vector by dividing by its magnitude, and you take the dot product of the gradients and the direction vector. That dot product is your slope, that's your directional derivative. That is the end of today's lesson. If you feel like this was not enough examples, I'm a little worried that this was too much theoretical exposition and not enough actual worked examples. If that is the case, please leave a comment, let me know. I can create some more videos for this if you like. For now, I'm going to call it a day.